Okay, so in this video, we're going to look at binary operations. So binary operations arise naturally in various branches of maths, including group theory, ring theory, and linear algebra, for example. In this video, we will look at the definition of a binary operation, as well as some examples and some non-examples. So a binary operation on a set S is just a function, which we call f here, from S cross S to itself. So all this means is it takes two elements of S and maps them to another element of S. Okay, so we'll introduce some notation here. Often, instead of using the letter F or a letter for the function, we use this symbol, a star, for the binary operation. And instead of writing f of AB for two elements of S, we'll write A star B. So this is standard notation when you're dealing with binary operations. So let's look at some examples of binary operations. So the first example, we take S to be the real numbers, and we take F to be the function on R cross R to R, defined by f of A, B is equal to A plus B. Or, in our notation that we introduced above, we would just say that A star B is equal to A plus B. So we see here that addition is a binary operation on the real numbers. We take any elements A and B, which are both in R, and we can define a number A plus B, which itself is in R. So the important thing here is that it's a well-defined function and all the elements are mapped back to the set itself. Another example we could look at would be the n by n matrices with real entries. Once again, we could define F from S cross S to S to be f of A, B is equal to A plus B, or in our other notation, A star B is equal to A plus B. And once again, you can see that this is a binary operation. If we take two matrices, two n by n matrices with entries in R, say A and B, then the sum of these two matrices, A plus B, will be an n by n matrix with entries in R. Now let's look at some maps which are actually non-examples of binary operations, so maps which are not in fact binary operations. So if we take S to be the integers Z, and we define f of A, B to be A divided by B, or once again in our other notation, A star B to be A divided by B, then this is not a binary operation. Why? Well, the problem here, the first problem we run into, is that we can't divide by B if B is 0. And because we've taken S to be the whole set of integers, Z, then we still have 0 in the set, so this is undefined if B is equal to 0. We could try and make amends here and change the set to not include 0. So this notation just means Z without 0, so 1, 2, 3, 4, minus 1, minus 2, minus 3, etc. Then this function does become well defined, but it's still not a binary operation. Why? Well, if we take two integers, A, B, non-zero, then in general, A divided by B is not in this set. So for example, if we take A is equal to 1 and B is equal to 2, then f of 1, 2 is equal to a half, and this is not in the set. So this really emphasizes the important fact that the binary operation must take 2 points in a set and map them to a point in the same set. So to finish the video, we'll look at one more example of a binary operation. And this example is a bit more complicated and abstract than the examples we've looked at before. So firstly, we take a set X, and then our set S in our notation that we've been using is going to be the set of functions from X to X. So our set S is itself a set of functions from X to X. And then we're going to define an operation called composition on X by, what we're going to do is we're going to take two functions, so say g and h in S. So g is a function from x to x and h is a function from x to x. So both g and h are in the set S. Then we take our binary operation star. In our notation of composition, we usually write this as like a little o, like this. We define g star h, or g composed with h, by g composed with h. And to define a function, we need to say how it acts on elements of x. So for elements of x, it acts as g evaluated at h of x. So first we apply h, and then we apply g. And we can see that if you take the function h and you apply it to x, then you end up back in x, because h itself was a map from x to x. So now h of x is in big X, and now we apply g, and g maps from x to x. So g composed with h is again a function from x to x. So g composed with h maps from x to x, i.e. g composed with h is in our set S. So g composed with h is a function from x to x. So composition is indeed a binary operation. We've taken two functions, g and h, in the set S, and the operation of composition gives another function in the set S.